Hi everyone, my name is Aviad Levis. I'm currently a postdoc at Caltech. Unfortunately, I was not able to make it in person, so here is my recording about a collaborative effort between all the groups and individuals listed here to advance cloud remote sensing into 3D and go beyond optical properties to retrieve microphysical properties of these three-dimensional clouds. Now I want to start with some background and motivation for cloud tomography. As many may be familiar with, the typical operational retrieval is done by processing pixels individually or within a neighborhood to transform radiances or stokes into recovered cloud properties. These properties could be, for example, the optical density or effective droplet radius of a cloud. Now, these pixel-wise operations could be a lookup table, a linear set of equations, and increasingly, this could also be a machine learning algorithms. While this is the bread and butter of a lot of research, there are some well-documented problems with this paradigm. One major drawback is the retrieval biases associated with horizontal transport, which is unaccounted for in the model. This is especially acute at the boundaries, making it difficult to study cloud processes that are arguably most interesting at the boundary, like mixing, entrainment, and cloud aerosol interactions. Another key problem is that even if the retrieval were unbiased, this is not trivial to determine where within the cloud the retrieved properties are located. These column-integrated retrievals make it difficult to study spatially variable cloud processes and create a disparity between the retrieved quantities and cloud models. So today, I want to talk about a completely different way to look at clouds as 3D volumetric objects. In this paradigm, multiple views of the same cloud enable recovery of cloud properties on a 3D grid. The retrieved properties could then directly inform cloud models and give insight into spatially variable cloud physics. This is what I mean when I say cloud tomography. Now, cloud tomography is similar to medical tomography, where multiple X-ray views of the human body are used to get a non-intrusive volumetric image. In the past several years, we've developed a tomography that can use multi-view, multi-band, and in a more recent work, also polarization measurements to recover the droplet distribution within a cloud. Now, a key difference between cloud tomography and medical CT is that in medical CT, the ability to align source detector pairs around the patient enable measurements of mainly the direct transmission, and this gives rise to a simple linear inverse problem. Now, there are still many challenges for cloud tomography to become a reality. Nevertheless, the key computational challenge we tackled has opened the door to this area of research. We can now retrieve a 3D volumetric field that is consistent with 3D radiative transfer across multiple pixels, views, bands, and polarization measurements. Okay, so far I covered the what and the why of this talk. And before I outline the how, I want to talk about another critical point. Why now? I'm of the opinion that now is the perfect time for this technology to take shape and mature for two main reasons. The first is computational power. The increase in computing power is allowing us to consider increasingly nonlinear and complex problems. It could very well be that we would never be able to retrieve fine-scale 3D cloud structure at a global scale. Nevertheless, cloud tomography will undoubtedly open up a new window of observations into spatial variability of clouds. The second key technology that could be a game changer is small satellites. With short development times and low costs as compared to traditional satellites, this technology could enable spaceborne multi-view systems to support large-scale tomography of clouds. Cloud CT, for example, is a multi-view mission spearheaded by my PhD advisor Yoav Shechna, which is dedicated to cloud tomography. In brief, the mission concept comprises of a formation flight of coordinated cube satellites that will acquire simultaneous multi-views of clouds. The goal of Cloud CT is specifically tailored to small cumulus clouds, which are a blind spot in remote sensing. Now, while Cloud CT is still in the planning phase, and even before the concept was created, our initial computational advances largely focused on data and simulations of JPL's AR-MISPI. The computational question we were initially asking was, can we use the 9 views of AR-MISPI to retrieve a 3D volumetric distribution of extinction? That is, how dense is each voxel or volume element within a cloud? Now, we tackled that question by formulating an optimization problem where we fit an image formation model or forward model to multi-view measurements, here denoted by Y. The optimization is solved by iteratively adjusting the estimation of cloud properties in a gradient-based optimization until the model outputs match the AR-MISPI measurements. And before I describe how we solve this minimization, I want to briefly describe the image formation model. In a single scattering model, we account only for the surface reflection coming from the tree and volumetric scattering of sunlight into the line of sight. However, clouds exhibit multiple scattering interactions. Therefore, not only sunlight scatters into the line of sight, but rather light from every direction. One key insight of our work is that we could make the optimization tractable by decomposing each optimization step into 2 components. In a high level, the first component captures the dependency on the optical properties along the line of sight. The second component captures the multiple scattering dependency using a full 3D RTE computation. With this in mind, we devised an iterative scheme. Starting off with an initial guess of cloud properties, beta 0, we compute this J, which is the multiply scattered radiation from every point at every angle. Computing J is a forward time-consuming recursive problem of solving the 3D radiative transfer. Now, this J is sometimes called the source function, which is a key output of Evans's SH dome. In the next step, by fixing J everywhere, we update the cloud extinction beta by solving an inverse non-recursive problem, which is quick to compute. This tomography problem only involves computations along lines of sight from every pixel, which is analogous to the medical computed tomography I mentioned at the beginning. We alternate these 2 steps until convergence to get an estimate of the cloud properties on a 3D grid. Now, this is sort of a hand-wavy explanation, but if you're interested in more details, you can see our paper from 2015. Okay, so far I've described the problem in terms of recovering the 3D extinction within a cloud. However, we would like to go beyond optical properties. We want to know if at one point there are many small droplets and at another point there are less droplets but they're bigger. Now, both of which may give rise to similar optical density, but will have a distinct phase function. The droplet sizes can be characterized by an effective radius and liquid water content, and retrieving these microphysical properties is key to advancing our understanding of cloud processes. So, how can we use linearly polarized signals to help in retrieving the droplet sizes? Well, we know from Mie theory that phase function depend on the droplet size distribution. Here, for example, is a polarized Mie component for 3 different effective radii zoomed in on the angular region of the cloud bow. The position of these cloud bow peaks clearly depends on the droplet size. So polarization, therefore, can help improve the sensitivity to the phase function by eliminating the multiply scattered component of the signal. In this beautiful work by Brion and Golub, they showed how the cloud bow becomes salient in polarization using polar measurements. The polarized signal removed the backdrop of the unpolarized multiply scattered light. This principle was also demonstrated at the much finer scale of AR-MISPI. Okay, so polarization gives us sensitivity to particle sizes, and intensity gives us sensitivity to the overall mass density. And we could come up with some heuristic way to separate the two signals and do an optimization separately for each one of those. However, this separation would be artificial. So we would like a unified framework to extract both the size distribution and the liquid water content jointly from all orders of scattering. So, relying on the iterative scheme I described before in replacing the scalar SH dome with the polarized vector SH dome, we're able to jointly estimate the effective radius and liquid water content in 3D. But just because you can doesn't mean you should. And so, to reduce the degrees of freedom in our simulations, we assumed that only the liquid water content is three-dimensional. However, the effective radius is a 1D unknown function of altitude. In the paper, we quantitatively assessed our approach using LES simulations. We simulated realistic air-MISP polarimetric measurements with realistic noise based on sensor parameters and compared the recoveries of the liquid water content and the 1D effective radius. We also demonstrated our approach on real air-MISP data from a Pacific campaign. Here we don't have access to the ground truth data. However, we assess the recovery using cross-validation. Leaving out one angle from the optimization, we can recover the 3D cloud properties, and then we can use the recovered cloud to simulate the left-out image using polarized SH dome, and we can compare that with the acquired air-MISP image. Here, in the top row, I showed the acquired air-MISP Stokes component from left to right, I, Q, and U. And in the bottom row, I show simulated views that were not included in the optimization. You can appreciate that there are many similarities here. In the last part of the talk, I'd like to talk about some recent and upcoming directions for research. In particular, I want to highlight this work spearheaded by Jesse Loveridge that analyzes and improves both theoretical and numerical aspects of cloud tomography. Everything that I described earlier today was sort of a hand-wavy explanation, and conveniently, I showed results from optically thin cumulus clouds. But how does the optimization approach handle optically thick cloud properties? This illustration by Jesse shows a decrease in sensitivity with optical distance from the sensors. Jesse shows that extra care should be given to minimize recovery biases in an optically thick regime. Moreover, over the years we've spent a lot of effort coding, documenting, and recoding so that our code will not only be available but also useful. I wrote at least 3 versions of this code, but the latest version, led by Jesse, is definitely the best version yet, so I urge people to try it out. Lastly, I want to highlight the works of Yael Stechen and Roy Ronen from the Technion that are making cloud tomography faster. So how do they achieve the significant speed up? Well, in 2012, a meteor in the form of deep learning crashed into the computer vision community. It took the shockwave some time to reach many other science fields, but in the last couple of years, the impact of deep learning is felt throughout many, if not all, of the scientific disciplines. In this work by Ronen et al., they showed how comparable accuracy can be achieved at orders of magnitude speedup using a learning-based approach. This type of speedup is crucial for cloud tomography to scale up from isolated clouds to wholesale cloud fades. Thank you very much. I hope you enjoyed this talk.